So let's wrap up chapter 1 with section 1.9, free groups, free products, and generators and relations. So the material here is also covered in the Fraley book, the senior level book, in sections 39 and 40. We'll mention in passing some of the notation they use there and how it contrasts with the way we're approaching it here. The approaches are basically the same. The notation's a little bit different. We'll define a free group on a set and show that this idea of free is consistent with the idea of free on a set that we had in the category theory stuff as given in definition 1.7.7. We talked about the idea of free on a set in a concrete category. Concrete categories, you'll recall, were where the objects were sets, the morphisms were set functions. We'll also define generators and relations in a group presentation. So the really big topic from this section is group presentation. The other stuff is sort of equipment to get group presentations processed. Okay, to define a free group F on a set X, we'll first define words on the set and have a way to reduce these words, define a method of combining the words. This will be the binary operation in the free group that we'll produce, and then give a way to reduce the combined words. The free group will have the reduced words as its elements, and the combination is the binary operation. If X is the empty set, we'll take the free group to be the trivial group. Okay, so there'll be a bit of technicalities in this, in that we'll multiply two words together, two reduced words, whatever that is, and the product may not come to us initially as reduced, so we'll have to have a technique to reduce the product. And the elements of this free group will be reduced words. So we'll start with a set. Definition, let X be a non-empty set. Define the set, and I make up words as I go along. Let me pronounce that X inverse. Define the set X inverse to be disjoint from set X, having the same cardinality. Choose a bijection between the two sets, can be done since they have the same cardinality. Denote the image of lowercase x in set capital X as lowercase x inverse. And finally, introduce a symbol 1 that's contained in neither X nor X inverse. So we'll be dealing with the symbols, maybe call them letters because we're going to make words out of them, symbols from set X inverse, and the symbol 1. A word on set X is a sequence, an infinite sequence for now, A1, A2, and so forth, such that each A sub I is from the collection, the set of letters, if you will, X, X inverse, or the symbol 1. And such that for some natural number n, we have A sub k equals 1 for all k greater than or equal to n. In other words, at some point, lowercase n, the letters become 1s and remain 1s forever, as it were, for all values of the index greater than or equal to lowercase n. So these terminate with a tail of all 1s. So there's some kind of finiteness to it. It reminds me a bit about weak products to a degree. We won't discuss weak products in this stuff. What we're dealing with is something that's involves an infinite sequence, but ultimately there's some type of finiteness involved, this idea of ending with all 1s. The sequence that begins with 1 and is always 1, sources will correspond to an identity at some point, but we'll refer to this initially at least as the empty word, and sometimes we'll just denote it as a 1 as well. So there's what the words are. Let's illustrate that a little bit. Suppose set X as a symbols X, Y, and Z, then X inverse, the set would consist of the symbols X inverse, Y inverse, and Z inverse, and we'd have the symbol 1, or the letter 1, as it were. on the table as well. An example of a word then would be the infinite sequence x, x1, x1, x, x, x inverse, x inverse, x inverse, x inverse, y, 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 x inverse, and so forth. And then we hit the ones and stay with the ones. Not that there couldn't have been ones earlier in the word, but eventually nothing but ones. We'll treat these as if they were products, finite products, by dropping this latter stuff. And then you'll be very tempted to do some simplification of the x inverse and the x inverse and the x, right? And that's what it'll mean to reduce a word. So a word, A1, A2, on set capital X is reduced provided for all x letters. X and x inverse are not adjacent. In other words, if a sub I equals x, then a sub I plus 1 does not equal x inverse. And if a sub I equals x inverse, then a sub I plus 1 does not equal x. So in other words, there is no consecutive x followed by an x inverse or an x inverse followed by an x. We see right here, as well as right here, that that's not a reduced word in the previous example. And also a sub k equals 1 implies that a sub I equals 1 for all I greater than k. In other words, as soon as one of the letters is 1, it's nothing but ones from there on out. Another reason this isn't a reduced word, there's a 1 followed by a non-1 and another 1 followed by non-1s. So not reduced in addition because of the presence of these two ones. Like I said, we'll treat them as products. Think of them as products and then do the obvious kind of reduction, dropping the ones and eliminating x and x inverses, for example. The word in example 1 is not reduced if we interpret this sequence W as a product of entries. It would be tempting. So, okay, we'll formalize it here shortly, but this is the idea. To eliminate the products giving 1 and then to drop the ones. So, claim is that word in example 1 can be reduced to x, y, 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 x inverse. Let's see if that's plausible. Okay, here we've got some ones we can drop. Here's an x inverse, x inverse, x inverse, x inverse, 4 of those. Here's an x, we'll drop the 1, and a x and another x. So there's 1, 2, 3, there's 4 x's followed by 4 x inverses. We could replace that with a 1 and then omit it. Here's 3 y's. That left us with an x over here followed by 3 y's. Claim down here was we'd have an x followed by 3 y's. Then an x inverse. Here's an x inverse and an x. We can drop. Here's a z and a z inverse. Here's getting a 1 and dropping it. And then we'd have a z and another z inverse, if you like, 2 z's followed by 2 z inverses. So we lose everything except for this x, these 3 y's, and this x inverse. And we keep those 3 things there, right? These cancel and these cancel, as it were. So we'll sort of interpret this word, associate this word with this reduced word. So we'll need a notation that allows us to make those translations as well. So for every non-empty reduced word of the form x sub 1, lambda to the 1, x sub 2, lambda to the 2, and so forth through x sub n, lambda sub n, and then it's all 1. So if this is a reduced word, one comment here, we're taking the exponents to be plus or minus 1s. So there's only x's and x inverses. There's not x squares. There's not x to the negative 2s, not in Hungerford. So from now on, we'll represent reduced words by dropping the 1s, eliminating the parentheses, and we would rewrite this reduced word in terms of just these symbols here. Remember, the exponents are plus or minus 1. Quick little comment, if you have some background in Fraley's book, Fraley allowed integer exponents. So Hungerford says we have xxx, or x to the 1, x to the 1, x to the 1. Fraley says we'll write that as x cubed. So we're not dealing with that notation. We've got exponents of 1 or -1, so that means repeatedly writing down symbols as opposed to collecting them together and getting integer exponents. So denote the set of all reduced words on set X as f of x. So f of x will become a free group ultimately. Right now, we know what the elements of f of x are. It's reduced words on set X. So it's reduced words where the letters, if you will, in those words, the symbols come from X, capital X inverse, or possibly 1. I mean, we only need the 1 symbol when we deal with an empty word, ultimately, because we've dropped it in all these reduced word representations. So in this new notation, 2 words, x's, subscripted x's with exponents of subscripted lambdas, and subscripted y's with exponents of subscripted deltas. Again, the exponents are plus or minus 1. These 2 words are equal if and only if both of them are 1. That'll always stand out as kind of an oddball case. Or if m equals n, the links, as it were, is the same. The last one here had a subscript of n, the last one here has a subscript of n, so m equals n. And the corresponding letters, x sub I and y sub I, are the same, and the corresponding exponents are the same. So they're equal if they're identical in terms of the letters used and the exponents used. In this way, each element of set X can be thought of as an element of f of X, a reduced word. It's a reduced word. I'd really like to say a reduced word of length 1. It's only got 1 letter in it when we drop all the 1s. So individual elements of X can also be thought of as words of length 1, if you will. And X can be thought of as a subset of f of X in that sense. So we need a binary operation on the reduced words. To define the binary operation, we need to ensure that the product of 2 reduced words is itself a reduced word. And we'll simply place one word after the other and then cancel things that can be canceled and drop, XX inverses, YY inverses, and so forth. So let capital X be a set, let f of X the set of all reduced words on capital X. The words 1 and W in f of X for these words define 1 times W equals W times 1 equals W. So that makes the empty word ultimately the multiplicative identity in this free group that we're creating. For words, subscripted x's with superscripts of lambdas and subscripted y's with superscripts of delta, n letters with the x's, m letters with the y's in general. So here's 2 words, reduced words, sorry. In f of x, being in f of x implies they're reduced. We first consider the word formed by juxtaposition, that is, placing one after the other. So it won't be a surprise, this binary operation we're defining won't be commutative. So we'll first take the word with the x symbols and follow it with the word with the y symbols. So that produces simply this word. I'm okay, I guess, in calling this a word. It's not a reduced word, maybe, because we could have some cancellation. The last term in X could cancel with the first term, the last term, the last expression in the first word could cancel with the first expression in the second word. The X sub n, lambda sub n could cancel with a Y sub 1, delta sub 1. These could be inverses of each other, possibly. Well, actually, then the second to the last one over here could cancel with the second one over there and so forth. So what we have here is not a reduced word necessarily. So we need a process by which we'll reduce it. First, suppose n is less than or equal to m. So this has less symbols in it than the second word has, less than or equal to. Let k be the largest integer such that x sub n minus j, lambda to the n minus j, equals y sub j plus 1, delta to the j plus 1, with an inverse thrown in, a little negative sign up there in that exponent. For example, when j equals 0, we'd be interested in x sub n to the lambda sub n, that's this term here, and y sub 1 to the negative delta sub 1, this term here. So what they're saying is if these two terms are inverses of each other, it's actually said the inverse of the y is the x, is how it's written there. But these are inverses of each other, then we need to drop them because we don't have a reduced word if that's the case. Oh, and it could be in j equals 1, the next pair, right? The second one in the second word and the second to the last one in the first word, and so forth. And so suppose that this relationship holds for j equals 0 through k minus 1. So we got k terms we need to simplify. Then reduce the juxtaposition to the following. So I plug in j equals k minus 1. Maybe we'll look at the subscript on the y's, are a little bit easier to process. So the last y letters canceled, that is when j equals k minus 1, would be y sub k. So we'll pick the y's up at y sub k plus 1, y sub k plus 2, and so forth. The x's, okay, it's the same story. We're going to cancel k of the x's. The last x canceled will occur when j equals k minus 1. That would give us n minus the quantity k minus 1. The thing that precedes that is n minus k. So the last x not canceled is the one with subscript n minus k. There we go. So we've reduced it in the obvious way by dealing with inverses, producing ones and dropping them. This being valid if k is less than n. If k equals n, then we actually cancel all of the x's. That's the reason it's broken into cases here. So we'd run out of x's in the event that all k of the x's were canceled. I mean, that's the reason we're considering separately the case n is less than or equal to m, and secondly, m is less than or equal to n. Do I run out of x's first or y's first when I get a lot of cancellation? Here we'll run out of x's first. In the second case, it's the same thing. If m is less than or equal to n, and we get this relationship between the inverses, then just cancel everything you can. In this case, the possibility exists that you'll lose all the y's and be left only with x's this time. If m equals n, we need the same kind of behavior. M equals n equals k, reduces to the empty word. So that's how you take a product of two reduced words and from it get another reduced word. So this process inputs two reduced words and outputs a reduced word. Well, then it's a binary operation. So the word produced through this is actually reduced, and that's what we'll use as the binary operation in what will ultimately be the free group f of x, free group on set x. As an example, suppose set x consists of the symbols x, y, and z again. Let's consider these two words. This time, notice they are reduced. X, x, y, y, z, z, x, y, z, and a bunch of ones. Z inverse, y inverse, x inverse, z inverse, z inverse, y inverse, z, and a bunch of ones. We'd take these and paste them together. So we drop the ones in the parentheses and all that stuff and juxtapose. So the last letter will be a z. Right here. Here's the first word in the shorthand notation. Second word, we'll drop the ones in the parentheses, and what remains is the second word. So there's step one, but it isn't reduced because there's a z inverse, there's a y inverse, there's an x inverse, a z and a z inverse, another z and a z inverse, a y and a y inverse. So let's see, we canceled everything except this last z, and we took out these symbols, right? These compose with the inverses to give an identity. We're left with x, y, z is given. It says, notice here that k equals 6. 6 is a number of terms, well, pairwise, number of pairs of terms that simplified to give us the identity. We've got y, z, z, x, y, and another z. There's 6, and then their inverses is listed here. So that illustrates how this simplification works. First theorem says, if x is a non-empty set, and f equals f of x is a set of all reduced words on x, then f is a group under the binary operation defined in the previous definition. So really is a group under this binary operation. Also, f is generated by x. The group f of x is called a free group on set x. We'll relate it to the category theory stuff and the idea of free there in the next theorem. But let's look at a proof of the first one to establish that we actually have a group. Okay. First, the empty word, one, the infinite sequence of ones. This is the identity. We define the binary operation, so that would be the identity. Also, the reduced word, x1 to the delta 1 through x sub n to the delta n, has the inverse, x sub n to the negative delta sub n, x sub n minus 1 down through x sub 1 to the negative. And just put a negative sign on those exponents. Remember, the exponents are plus or minus 1. And then there's the two-sided inverse, so easy enough. Associativity is a touch more complicated. Okay. For any letter, any symbol x in set x, delta plus or minus 1, we're denoting a mapping. I'm going to read this for lack of more insight on my part. I'm going to read this the absolute value of x to the delta. But it's going to be a mapping from f to itself. Given by the mappings, take the empty word and associate it with x to the delta. X to the delta is an element of set f. F of x is it's a reduced word. And take the reduced word x1 to the delta 1 through x sub n to the delta sub n and associate it with these things. Okay, symbolically it's a lot, but what it really is you're just multiplying on the left by x to the delta. So this mapping takes a reduced word and multiplies it on the left by x to the delta. So we get x to the delta, x1 to the delta, x1 to the delta 1 through x sub n delta to the n, if x to the delta doesn't equal x1 to the negative delta 1. If these don't simplify, we can't reduce, in other words, this is a reduced word. If this is a reduced word, then that's what we get. If you multiply on the left this expression by x to the delta, and x to the delta is the inverse of x sub 1 to the delta sub 1, then simplify and eliminate those two. If you only had one term here, if n equals 1, you only had one term, x sub 1 to the negative delta sub 1, x sub 1 delta sub 1, and x to the delta was the inverse of that, then this will simplify down just to the identity. N equals 1, we only had one term, and it was the inverse of this. So what the mapping really does, more tangibly, it multiplies a reduced word by x to the delta on the left, and then you reduce it according to the way we reduce words, and produces a resulting reduced word. So it indeed is a mapping from f of x to f of x. The reduced words on f, on set x, the reduced words on set x to the reduced words on set X. It is a mapping of that sort. As it says on the next page, yeah, this just multiplies on the left by X to the delta and then reduces. The fact that it does that allows us to find inverses of these mappings. All of a sudden, it's a conversation about mappings. The absolute value of X, X to the 1, followed by the absolute value of X to the negative 1 will be the identity. Actually, I should read from right to left because this is actually function composition. So what we would do is multiply on the left by the symbol X to the negative 1, and then multiply on the left by the symbol X. Well, those two would cancel out when we do the reduction, and we just end up with the original word. Similarly, if we multiplied on the left by X and then multiplied on the left following that by X inverse, reduction would lose those. And we get that these two mappings are inverses of each other. More generally, if we take X to the delta, absolute value of X to the delta, that particular mapping preceded or followed by the absolute value of X to the negative delta, we're going to get the identity as well. So each mapping, X to the delta, has a two-sided inverse. X to the negative delta is a two-sided inverse, or absolute value of X to the negative delta. Corollary 0.3.b says if you have a mapping with a two-sided inverse, then that mapping is a bijection. So all these things we define, these absolute values of X to the delta, these are bijections on F, or F of X. And so they're a permutation on this set of reduced words. So let A of F be the group of all permutations of F. We've used those symbols before, at least in passing. So A of F is the set of all permutations on set F. Here the set is the reduced words based on set X and X inverse and the symbol 1. So let A of F be the group of all permutations of F, and let F sub 0 be the subgroup of F generated by the set absolute value of X as X ranges over set X. So this is, I want to say it's like half of the mappings. It involves half the letters, roughly. It doesn't involve any of the X inverses, and it doesn't involve the symbol 1. So we're taking a subgroup generated by this collection of mappings. So this would involve always multiplying a reduced word on the left by X, an element of capital X. Consider the mapping phi from F to F sub 0, given by phi of 1 equals 1 sub F. So we'll define it as such. Remember, we're dealing here with a mapping from F to F sub 0. All these other things are mappings as well. So saying we get the identity on F says if we'll take in an element here, it simply produces the same element as output. That's the way we're defining the phi function. And phi of the reduced word, X sub 1 to the delta sub 1 through X sub n to the delta sub n, define that to be this composition. So this phi maps reduced words to permutations of F. Permutations given by multiplying on the left and then doing the reduction. F sub 0, by definition, is generated by these permutations. Okay, well, it's a generating set. Then the elements of F sub 0 are these things and these things to any power, as it were. So what we'll get out is in F sub 0, elements of the form X sub 1 to the delta sub 1, where delta's 1 or negative 1, using the fact that we're dealing with these as mappings. So when we take an inverse, we get an inverse mapping. And we've seen upstairs the inverse of the mapping absolute value of X is the mapping absolute value of X inverse. The fact that F0 is generated by these things and we went into a group of permutations, so I can talk groups in this setting, allows us to include the mappings with the -1 exponents. So the elements of f sub 0 will be of this form. It would be products of powers of the elements in the generating set. And that's what Theorem 1.28 tells you that elements of a group look like. They're integer powers of elements of the generating set. Okay, we don't have explicitly the squares written here, but if I get a absolute value of x squared, of course that's an absolute value of x repeated. Right? So I do repetitions to get exponents other than 1 or -1, but we can still get that type of representation. Phi is onto f sub 0. Yeah, because f sub 0 involves the permutations generated by this set here. Any one of these things is certainly an element of something. If this is in f sub 0, this is the image of x1 to the delta 1 through x sub n to the delta n, because that's how I'll define the mapping. So I know what the elements of f sub 0 look like, and I know they're images of something in f itself. All right, so what's left to show is, do we have a homomorphism? We claim phi of W1, W2 equals phi of W1, phi of W2. It's just a computational thing. This may take a little while to get through. Notice W1 and W2 is reduced. And so some of the terms on the right-hand end of the first word may have been canceled with some of the terms on the left-hand end of the second word, as we saw when we were doing the reduction. Say there's k such terms, and that's how we dealt with it in the reduction comments above. We said k terms from each word disappear. The reduction removes 2 k terms, k from the first word on the right-hand side and k from the second word, the left-hand side. Say the canceled terms are these: x sub k lambda to the k up through the last x, first y up through y sub n minus k plus 1 to the delta n minus k plus 1. Say these terms are canceled. Because these are inverses, the next pair is inverses. We get these pairwise as inverses. Well, then these must yield as a word the empty word, just the 1. That's the exact same thing we had before. But these are the terms that are canceling out because in our technique, we treat these as if they were 1. Now, technological boo-boo, there we go. Phi of 1 equals the identity on set F. That was how we define phi of the empty word 1. So if we apply phi to this representation of 1, that'll produce the identity on F. And when we apply phi to this, remember the phi simply took a reduced word and associated it with these particular mappings, these permutations. Right down here, we're actually in the group of all permutations on A of F, on set F, the set of reduced words. So this is what phi does to this reduced word. This is what, what it does to this word. It's not reduced, it reduces to 1. But that's what phi does to this, so that's what phi does to 1 because they're equal. So that gives us this type of relationship between the mappings and the identity functions. W1, W2 has a representation. Here's W1, here's W2. Juxtapose, just replace the y's after the x's. Before the reduction, it looks like this. After the reduction, you've lost all this stuff in the middle here. So I've lost, the x's starting at x sub k. The last x here is x sub k minus 1. And we've lost the first y's up through here. The next one would be what? N minus k plus 2. Yeah, y sub n minus k plus 2 to the last one. So after the reduction, we get something like this, with the usual caveats about, well, all of the x's could have disappeared, possibly all of the y's could have disappeared, possibly. The whole thing could have disappeared and left us with an identity, in which case we've already taken care of things upstairs. But we get W1, W2 looking like that. And the goal was to show phi of W1, W2 equals phi of W1, phi of W2. Remember, we're trying to show f, or f of x, actually as a group. We're working on associativity and all this stuff. So if we take phi of W1, W2, that would be what we had from before. The first bunch of x's was with the last batch of x's omitted. The first corresponding batch of y's omitted, and then the rest of the y's. So W1, W2 as a reduced word had these symbols involved. So phi turns those symbols into mappings. That's what phi did. Now, I'll tell you what, let's stick this in between the last x and the first y. Stick this in. This is the rest of the x's and the first bunch of the y's. Because we saw upstairs, well, the product of those as mappings is just the identity function on f. So we've stuck the identity in between the last x and the first y and written it in this form. The right hand of these equations, these deal with permutations, right? These are permutations in the group A of f, as we denoted it above, group of all permutations on set f. So we stuck an identity in. The procedure, the operation here is permutation composition, so it's function composition. We can deal with associativity in the function composition, and we can associate all of the x's together and all of the y's together to produce this. And this is phi of x, and this, phi of W1, and this is phi of W2. And so we have phi of W1, W2 equals phi of W1, phi of W2. So phi is a homomorphism. Okay, so where are we here? We're trying to show f as a group under the binary operation that we introduced. We know there's an identity, we know there's inverses, and we're working on associativity. Associativity of the binary operation. Here, we've shown phi is a homomorphism. All right. Let's look at something which by phi is mapped to the identity. All right, we're trying to set up a group isomorphism here. If I know we have a one-to-one and onto homomorphism, I know we have a group isomorphism, and that's how, still the goal is, how we're going to get associativity in this alleged group f, or f of x. So suppose phi maps this word, this reduced word, to the identity in the group A of f, the group of permutations. Then the image of this reduced word is, as I've read it, absolute value of x1 to the delta 1 through absolute value of x sub n delta sub n. That's what phi does to that reduced word. It produces this mapping that must equal the identity on set f. In group f sub 0, the group generated by the absolute value of x ranging over the axis elements of set x. The inverse of the mapping, absolute value of x to the delta, is absolute value of x to the negative delta. So the only way we could get the identity here is, remember these deltas are all 1 or negative 1. The only way this could give us the identity permutation is if pairwise we get these things to reduce. Whatever one of them does, the one preceding or following it must undo. So that's the only way we can produce the identity in terms of these permutations. In other words, we get these to reduce down to the identity mapping. The only way that happens is using these types of inverses here. Well, of course, forget the absolute value mapping stuff, x to the delta and x to the negative delta these elements, or these words of length 1, these are inverses of each other as well under the binary operation. So if we get this to reduce to the identity mapping, we must have this product to reduce to the identity in F. In other words, the only thing mapped to the identity by this mapping phi is the empty word, the identity in F. The kernel of phi is the identity in F, the empty word. So, hey, if the kernel consists only of the identity, then we got ourselves a one-to-one mapping. Theorem 1.2.3 part 1, many times we've looked at the kernel of a homomorphism to see if it was trivial. And if so, then we know the mapping, usually a homomorphism, is, or at least a homomorphism. The homomorphism is one-to-one, is injected. So that's the case here. We need to establish onto-ness. We'll have one-to-one and onto-ness, then we'll know we'll have an isomorphism. F sub 0 is a group. The binary operation on F sub 0 is associative. Phi is a one-to-one mapping. And onto, let's see, where do we establish the onto-ness? It's got the homomorphism property. So it actually must be a group isomorphism. So F is a group, it's associative because of this isomorphism property. The onto-ness, I guess we established that really early on. Said you give me an element of F sub 0 and I can find something that is the mapping, that is mapped onto it. Let's go back and find that, the onto-ness, but we did that earlier. This is a lengthy proof. F is generated by the X's, the alphabet of group F. So we said something about the generators here. So of course, that means F is ultimately determined by the symbols in set X, X inverse, and the symbol 1. But that's what it means when we say F is generated by these symbols. The inverses and identity come along with that. And I was worried about onto-ness. Excuse me, we probably did that at the very beginning. Yeah, here we go. I know what the elements of F sub 0 look like. They look like this. And this, of course, is the image of something of that form. Drop the absolute values. It's more sophisticated than that. These are permutations, and these are words over here. But anyhow, of course, we get this reduced word to be mapped to this permutation, and there's the onto-ness. So let me get it ready for the next one and go back to the notes. Some properties of free groups we claim is the following. We'll quote some justifications of these. First property, if set X has at least 2 symbols in it, then the free group on X is non-abelian. Argument for that one, let's actually go through that right now. Property 1 holds, suppose we take X and Y as symbols that are different. You know, there's at least 2 things in X, so take 2 different symbols. The word X inverse, Y inverse, XY is reduced. Well, if it's reduced, then it doesn't equal 1. If it doesn't equal 1, then XY doesn't equal YX, right? Multiply on the left here by X and then Y. Same thing over here, the inequality will be preserved. And we get XY doesn't equal YX. Well, there's a non-commutivity. These were arbitrary different symbols, so we don't have commutivity in any of these free groups on 2 or more generators. Every element of a free group, except the identity, the empty word, has infinite order. By the way, that's to be shown in one of the exercises. Thirdly, if X consists of a single symbol, then the free group on X is isomorphic to the infinite cyclic group of the integers. This group generated by A is isomorphic to the integers. That's also an exercise. It's exercise number 2 in this section. Fourthly, every subgroup of a free group is itself a free group on some subset. So subgroups of free groups are themselves free groups. Hungerford describes this last one as a decidedly non-trivial fact and refers to Rotman's theory of groups. For the record, it's Theorem 11.23 in that book. I know that because I must have stumbled up on a copy of Rotman's book on the internet somewhere, so it's probably floating around out there in PDF form. But there's a few properties of free groups. As promised, let's connect free groups with the concept of free on a set from the category setting. Theorem 1.9.2 says, let F be the free group on set X, I, or iota, mapping X into F, be the inclusion mapping. So all this does is treat individual letters as reduced words, where the free group on set X is what we had just defined in Theorem 9.1. So this simply takes elements of the set and puts them inside the free group. It treats them as reduced words of length 1. If G is a group and F mapping X into G is a map of sets, then there exists a unique homomorphism of groups, F bar, mapping F into G, such that F bar composed with iota equals F. In other words, F is a free object on set X in the category of groups. Okay, let's take a look at that definition from section 1.7, the definition of what it means for it was a concrete category to be free on a set X. So let F be an object in a concrete category C, X a non-empty set, and I a set mapping. Okay, concrete categories, that's where the objects were sets and the morphisms were set maps, as they call it, functions between sets, which is totally what we have in our current setting. So we are in a concrete category, if you wish to interpret it as such. F is an object. Okay, we're taking the object from the category definition as this free group F in our current setting. Object F is free on this set X. Okay, the set X down here is the same as our set X up here playing the same role, provided that for any object A in the category, the set mapping X into A implies the existence of a unique morphism, F bar, mapping F into A, such that we get this composition as that type of mapping. We actually explained it, bring it up. We explained it in terms of a commuting diagram back when we were doing that. Oops, I don't want it, don't want exactly that. But let's match the pieces up again. Okay, so they said any object A, that's group G in this setting. So we've taken G a group, so any group G, we're in the category of all groups, so the objects are groups. So the A down here is being played by the role of G up here. Down here we had F mapping X into A. Up here we have F mapping X into group G. Down here it was a conversation about F bar mapping capital F into A. Here we've got F bar mapping capital F into group G. We get the same composition, we just didn't use a composition symbol here. So this, in the category setting of object F is free on set X, the claim by Theorem 1.9.2 is that's the same thing we got here. this free group on set X is actually a free object on set X in the appropriate category. That would be the category of all groups. Let's look at the proof of that one. Okay, so we need to establish something about a unique homomorphism. We need F bar in this setting. Okay, define F bar of the empty word to be the identity. Notice F bar takes us from the group of reduced words to this group G. So map the identity in the free group to the identity in group G. And for x1 to the lambda sub 1 through x sub n to the little typo there, lambda sub n, a non-empty reduced word on X, define F bar of that reduced word to be F. This came with a group G, and F, a mapping of set X into G. Right? These two things came to you. So F has been given to us, taking elements of set X and giving us out elements of group G. So F is defined on, in particular, x1 through x sub n. So define F bar of this reduced word as F of x sub 1. That's defined, its group element, to the lambda 1. If lambda 1 equals 1, it's just F of x1. If lambda 1 equals negative 1, it's the inverse of F of x sub 1 in group G. So this makes sense. So take the F of the subscripted x's and the corresponding exponents. So drag that delta. Both of these delta sub n should be lambda sub n's. I'll get that fixed in the online notes. F is a set function. G's group. So as I commented, these negative exponents, ultimately the symbols we've written here are well defined because we're in the group. It means inverse elements because we're mapping into a group G. Okay, we want to show F bar satisfies the homomorphism property, and we also need F bar to satisfy this composition property. So let W1 and W2 be reduced words. As in the proof of the previous result, when we juxtapose those, a bunch of stuff canceled. So as in the previous theorem and as in our definition of reducing a product, say these terms here are the terms that we lose in the reduction process and reducing down to a reduced word, the product W1, W2, the X's that are lost, the last X's on the right and the first Y's on the left in the second word that are lost. Let this be the canceled terms. By the way, that means this equals 1, the empty word, the identity in the free group. Then the product of the canceled terms equals the word 1, the empty word 1. And so in group G, by taking F bar of 1, we're taking F bar of that product. F bar of that product was defined as this, exactly as we had before, except now there's Y's involved, and same definition. So we simply take F of each of the letters and put the appropriate exponents on them. And you know, F bar of 1 is the identity. That was the first thing we defined. So what we get here is a product of elements of group G that produces the identity. And this involves the terms that were canceled. We're trying to show F bar as a homomorphism. So let's take F bar of W1, W2. This is similar to what we did in the previous theorem in the proof. Well, here is W1, W2. Of course, the problem is there's a bunch of stuff missing, right? We've lost a bunch of X's and a bunch of Y's potentially in the reduction process. But that's what W1, W2 is under the binary operation in the free group. So when we apply F bar to that, as above, that's F of the subscripted X's with the corresponding exponents. And the problem is all those middle terms are missing. But wait, let's introduce an identity in group G. So the only difference in this line and the next line, so I've introduced an identity after the last X and before the first Y. Hey, here's an expression for the identity here, and it involves all the missing X's and all the missing Y's. So for the identity here, replace it with the missing X's and the missing Y's as spelled out up here in terms of the F's. So that produces this. Notice all the X's are there, X1 through X sub n. All the Y's are there, Y1 through Y sub m. So we're in business. On the next slide, I'll just drop these parentheses. So dropping the parentheses, understood this is a product of the first times second line. This is all the X's, this is all the Y's. They've got the appropriate exponents on the appropriate group elements to say this first batch of f of x sub i's times lambda sub i's, that corresponds to f bar of W1, and the second batch corresponds to f bar of W2. So the f bar mapping simply took a reduced word and associated it with f values, f being that mapping we had into group G that was given in the hypotheses. So f bar of W1, W2 equals f bar of W1, f bar of W2. It's a homomorphism. We need to deal with a composition now. The inclusion map, iota, simply embeds the set of letters, X, into the set of reduced words. So it just changes the setting from set X into free group capital F. So I can use the group mappings then. In particular, I can use the F bars. F bar maps the reduced words to group G. So F bar iota maps set X first into free group F and then into arbitrary group G that they gave us. And it has a homomorphism property. By definition, F bar of iota equals F on set X. So if we take a lowercase x, apply iota to it first, that simply maps it from an element of set X into a reduced word in the free group capital F. And then F bar takes that little x and maps it to F of X. That's exactly what F bar does, as given, say, when it was applied to W1 here, except we'd only have a single X. If you like, we could view this maybe as a F restricted to set X, on set X is an alternate way of stating it, but we get this kind of behavior on set X. So we've got homomorphism. It satisfies the function composition. The only thing we're missing now is the uniqueness. If G bar is any homomorphism, mapping a set of reduced words F to group G, such that G bar iota equals F on set X, then we're going to show G bar and F bar are the same, and there's a uniqueness. So let's take G bar and apply it to this reduced word. Okay, we're dealing with a homomorphism. So G bar will produce G bar of X1 to the lambda 1 and so forth. We said G bar was a homomorphism. We know that G bar composed with iota produces the same value as G bar itself. We just described this on the previous page, except in the setting of F bar. F bar equals F bar composed with iota on set X. Let's go back to that. We had this composition on set X. Okay, so G will satisfy the same thing on set X. Actually, I don't need the bars on this right-hand side. That's a little bit of a typo too. I need to eliminate the bars from this. Something else I'll fix in the online notes. But then I get the G bar back on this. G bar iota equals G itself on set X. That should read. And we've hypothesized that G bar iota equals F as well. So we can replace the G bar iotas with F's, and that's the same as F bar of the word by definition. So F bar and G bar, they do the same thing if they satisfy those conditions, and that's where the uniqueness comes from. Okay, those are the two lengthy proofs, the first part of this at least. Back to one last comment about the category theory. Theorem 1.7.8 tells us that if in the concrete category C, object F is free on set X and object F prime is free on set X prime, or X and X prime have the same cardinality, then F and F prime are equivalent. Actually, let's look at that as well. Theorem 1.7.8. Okay, that just be down the road from this definition 1.7 a little bit. Here it is specifically. So when I take free objects on sets of the same cardinality, I get equivalent objects. All right, equivalence in the category of groups was isomorphism. So that translates in our current section as saying, if F and F prime are free groups on the same set X, then they'll be isomorphic. So this concept of a free group is unambiguous up to isomorphism. I could even replace set X with X prime. As long as the cardinalities of the sets are the same, then we'll get that the free groups are isomorphic. Okay, a shocking claim in corollary 1.9.3, it says every group something. And how many results do you know that state every group something? What it does is this links every group with free groups in the following sense. It says every group G is the homomorphic image of a free group. So we were just talking a bunch about homomorphisms and our definition of free group. Let's go through proof of that. Sounds like quite an accomplishment. Actually, the proof of this one is fairly brief. The hard work is in the previous results. So let X be a set of generators of group G. Such a set exists. Hey, all the elements of G generate G. So generating sets do exist. So let set X be some set of generators. Let F be the free group on set X. Okay, that's well defined in terms of the words and the binary operation and all of that. The inclusion map, iota, mapping X into G, is such that X, a symbol, a letter from set capital X, is mapped to X, an element of group G, which simply does the embedding. So by theorem 1.9.2, we know there exists a homomorphism, F bar, mapping the free group into G, which maps X to itself in G. And since G is generated by those X's, we chose set X to be a set of generators, then F bar, hey, F bar is onto the generators of G, then F bar is onto all of G itself. That is, it's an onto homomorphism, it's an epimorphism. So F bar maps free group F onto group G. In other words, the image of F bar is G. F bar is a homomorphism. Group G is the homomorphic image of the free group. And the homomorphism is this homomorphism F bar defined above. So there were no constraints. I guess I could lay this at the feet and part of the category theory. It allowed us to choose any group, any object in the category setting. We were able to choose any group in theorem 1.9.2, and we created the homomorphism from there. Here, that's how we get to the every group statement in the corollary. Basically the same result, but let's state the following. Gallian is the author of a senior level algebra book, may or may not have mentioned the Gallian book in passing in here. It's sort of a competitor to the Fraley book. The Fraley book, in my opinion, is a good deal better. But this is something from the Gallian book. It's not the Fraley book, I don't think, which Gallian calls the universal quotient group property. And it says every group G is isomorphic to a quotient group of a free group. Okay, so we've shifted from homomorphic image to quotient groups. Have to have a conversation, no doubt, about normal subgroups. The proof for this one is so brief with the information we have. I just included it in the notes. Let G be a group. By the previous corollary, we know there's a free group F and a homomorphism F bar such that F bar of the free group equals group G. G is the image under that homomorphism of that free group. Let N be the kernel of that homomorphism. All right. The first isomorphism theorem told us, this center stuff here, told us when you have a homomorphism mapping one group to another, the image of that homomorphism is isomorphic to the input group mod the kernel of that homomorphism. First isomorphism theorem. I told you we get a lot of mileage out of that one. But the image of F bar is G. We know that from the corollary. The kernel of F bar, we've simply denoted as N. So we can write that as F mod N. Remember, kernels of homomorphisms are always normal subgroups of the domain group, as it were, the input group. So we can write G up to isomorphism as a quotient group of a free group and a normal subgroup of that free group. In other words, it's a quotient group of a free group. So there's, I guess, a reason to like quotient groups. And let me play this up a little bit again. I can't think of too many theorems that read every group G has the following properties, other than stuff from the definition. Every group is isomorphic to a group of permutations. Cayley's theorem is another every group theorem. But that and this couple of little things here, that's all I can think of off the top of my head, of results that read every group, blah, blah, blah. Okay, let's chat about this a little bit and introduce a little bit more vocabulary and talk about the thing I claimed I was most interested in is group presentations. The group presentations are based on generators and relations. So first note, by the universal quotient group property, as just mentioned from the Gallian book, group G is determined up to isomorphism if we know set X, group F, and the kernel N of the homomorphism that was guaranteed to exist. But group F is determined up to isomorphism by set X. So I know set X determines the free group. It's the letters that you use. The kernel of N is determined by a subset of group F, which generates the kernel as a subgroup of F. Okay, so this is where it becomes nebulous, in my opinion. All right, yeah, it boils down to knowing set X, the free group on that set, and the kernel. Well, set X we will take as ultimately we call them generators of free group F, and the kernel, well, it's describing the kernel, it's a tricky part, but it's determined by some subset of F that generates this normal subgroup, the kernel N of the homomorphism that we know exists, the F bar, say. If we take a reduced word and F is such a generator of N, then the homomorphism F bar maps that reduced word to the identity in group G. That's what it means to be in the kernel. What does F bar do to this reduced word? Well, as we just said, F bar maps the letters in X, set capital X, to themselves, right? We had, what was it, F bar composed with the iota mapping, the embedding mapping, equals F, and when applied on elements of set X, simply outputs the elements. So F bar is going to take the X sub i's to themselves. So we get F bar mapping this reduced word in this sense must be mapped to the identity because we said it comes from the kernel. This equation is called a relation on the generators x sub I of G. So we'll have generators of a group. They'll be the elements of set X. And we'll have these relations. They're equations involving the generators. So if we know set X of generators of group G and a sufficient number of these relations in order to determine the kernel N of the homomorphism, then group G is determined. It's not surprising that the choice of set X and the set of R of relations is not unique. Different relations may yield the same group. This is to be shown in a couple of the exercises that we can take generators and different generators in different relations and produce the same group. So there's multiple ways to produce a given group. By the previous note, we see that for any group G, there's a complete description of G in terms of set X and a set of relations. In fact, what we get then, the relations determining the normal subgroup, we get G as isomorphic to the free group mod that normal subgroup N. F is free on set X, and the set of relations determine the kernel N in terms of some of the generators. Well, does it go the other way around? We want to consider the converse. That is, given a set X and a set Y of reduced words on the elements of set capital X, is there a group G such that G is generated by set X and such that the relations as given here are valid? So we're using R for the set of relations. What we're doing, because these generators of the normal subgroup, remember, had to be mapped to the identity in a quotient group. But what we're getting then is taking those relations, those words, and setting them equal to the identity. I hate to bounce around, but let me go back to the previous note. It's this idea right here. We had the words set equal to the identity. So that's how these relations come to us in terms of determining that normal subgroup capital N. So the relations are of the form word equals the identity. And we'll let words range over set capital Y. So these are a collection of words, products of elements of set X. And it's understood we'll set those equal to the identity to produce the relations. The answer is yes. Given X and a set of relations, yes, that determines a group, provided certain little caveats here. And this is how we present a group. This is what a group presentation will be, as we'll formally define here in a sec. It's given by set X of generators and the set of relations, capital R. So the claim is, yeah, this works, provided we allow for the possibility that the elements of X may not be distinct. For example, suppose we had A, B as symbols, and we had A to the first power, B to the -1 power is a relation up here. So we get it as one of the words in this set R. Being in set R means that word equals the identity. So we get the A to the 1, B to the 1, AB inverse equal to the identity. We get this as an equation. But if that's the case, we can multiply both sides of the equation on the right by element B, then we get A equals B. So that relation forces us to conclude A equals B. And by the way, it turns out then A to the 1, B to the -1. This really wasn't a reduced word after all, because it turns out it reduces down to an identity. It must reduce down to 1 in a sense. So there's that bit of a caveat, but here's more details on this idea of generators determining a group, generators and relations. Let X be a set of generators, Y a set of reduced words on the elements of X. Group G, generated by set X, which satisfies the relations in this set R, as we had above, is constructed as follows. Okay, so here we're taking advantage of that theory that we've developed in this section so far. Let group F be the free group on X. Okay, we know how to deal with that. You take the reduced words, you use the binary operation that we described above. So no problems in establishing the free group on X. We have a uniqueness of that, well, you know, up to isomorphism. We made a comment about that earlier. And let N be the normal subgroup of F generated by Y, the set of words that determine these relations. So there's three sets. There's the generators in set X. There's the words in set Y that determine the relations in set R. So we want those words in set F and those words in set Y to generate a normal subgroup of F. So what we do is take, we dealt with this in one of the exercises in section 5, what it means to have the normal subgroup generated by a set of elements is to take the intersection of all normal subgroups of F that contain set Y. So that's what it means to generate a normal subgroup. Generating subgroups was similarly defined. Intersections of subgroups in that case, intersections of normal subgroups in this case. So that's what we take in terms of finding in the normal subgroup based on set Y, which determines the relations. And then we let G be the quotient group, F mod N. Okay, the next part's a bit less rigorous. First, identifying elements of the set with their images in F mod N. So identify set X with its image in F mod N under the canonical epimorphism. That is, for element lowercase x in this set, look at the left coset. Remember, of course, in a quotient group, of course, at this stage, in a quotient group, what we get is cosets of, I've said the denominator, cosets of n in this case. So we'll take element lowercase x, and the canonical epimorphism will map that to the left coset, lowercase x, capital N, left cosets, or right cosets. We're dealing with a normal subgroup here. But that's how we're identifying set elements with elements of this quotient group, using the canonical epimorphism. Taking x and putting it to the left of capital N and looking at that coset. So that's the identification that's done. We made some comments somewhere above that, okay, that's definitely not a one-to-one procedure, this identification. All the elements of X that are in the kernel of the homomorphism or the canonical epimorphism are identified together. In fact, any two elements of X that happen to be in the same coset of N will be identified together in this sense. Of course, any element of N itself is associated with the identity in the quotient group, is associated with the coset of N itself. So this identification is not a one-to-one procedure, but group G is generated by X. We chose X to be a set of generators of group G. Any relation W equals E in set R is satisfied because W, say it's expressed like this, will be in set Y, and the relations are W equals E. The canonical epimorphism is going to take that element W, it's going to map it to N. Remember, N is the identity in the quotient group. In quotient group F mod N, the identity coset is N itself. So the way we've constructed N will have that satisfied in terms of Wn. The canonical epimorphism will do toward W this, or if you like this, hey, if this is in N, we'll get N back out, and that's how we get the relation satisfied. So we have W equals the identity, W equals this word, equals the identity under the above identifications, and E is denoting the identity in the quotient group. It's capital N. That's what we mean by that. So the identification with that word is with capital N. And here's a formal definition of a group presentation, right? This was the goal of all of this stuff. Let X be a set, Y be a set of reduced words on X. A group G is the group defined by the generators in set capital X and the relations, W equals E, for W being that collection of words in set Y, provided G is isomorphic to F mod N, where F is the free group on set X, and N is a normal subgroup of F generated by Y. This is how the notationally groups are presented. So we'll give a presentation of a group as kind of like an ordered pair, X of generators and a collection of words, Y, which are ultimately interpreted in terms of relations. When we presented the dihedral group 2 or 3 sections ago, we had a result that described it as being generated by 2 elements, A and B, and we had relations between those 2 elements. A handful of equations involving those 2 elements. We actually had a presentation of the dihedral group, as we mentioned at that time. All right, so let's call it a day for now. I'll come back and elaborate on these group presentations a little bit. We got von Dick's theorem coming up next, and that gives some idea of how big a group presentation is. It's minimal in a certain sense, to be described here shortly. Have a nice day. We'll pick up on the rest of section 9. We're well over halfway through this section, and that'll wrap up chapter 1. I'll see you in the next one. Bye-bye.